Today we will study the related knowledge points of the semiconductor diode and its basic circuits. In the previous lecture we introduced the diode and its simplified models. In this lesson we will continue to introduce several basic circuits composed of diodes, as well as general methods for analyzing diode circuits. Unidirectional conductivity is the basic characteristic of a diode. Based on this characteristic, many application circuits can be formed, such as rectifier circuits, limiter circuits, and switching circuits. The rectifier circuit is one of the most widely used diode circuits. When a load RL needs to obtain a unipolar voltage from a sinusoidal excitation source Vs, this can be achieved by inserting a diode in series into the loop. Here we analyze the circuit using the ideal diode model. It can be seen that in the positive half cycle of Vs, the diode is forward biased and in a conducting state, with a forward voltage drop of 0 volts. So the voltage across the load equals Vs. In the negative half cycle of Vs, the diode is reverse biased and in a cutoff state, equivalent to an open circuit. The loop current is 0, so the voltage across the load is also 0. At this time, the entire voltage is applied across the diode, meaning the diode's reverse voltage equals Vs. It can thus be seen that this circuit converts the bipolar voltage of the excitation source into a unipolar voltage for the load. A circuit with this function is called a rectifier circuit. Since the load only obtains a waveform for half the cycle, this circuit is also called a half-wave rectifier circuit. Obtaining the entire waveform requires a bridge circuit. Now we will still use the ideal diode model to analyze this circuit. In the positive half cycle of Vs, point A has a higher potential than point C. In the branch from point A through D2, RL and D4, to point C, D2 and D4 are forward biased and conducting with 0 forward voltage drop. At this time, the potential at point A is higher than that at point D, and the potential at point B is higher than that at point C, causing D1 and D3 to be reverse biased and cut off. The circuit can be equivalently represented as in diagram B, and the voltage across the load equals Vs. In the negative half cycle of Vs, point A has a lower potential than point C. In the branch from point C through D3, RL and D1, to point A, D3 and D1 are forward biased and conducting with 0 forward voltage drop, while D2 and D4 are reverse biased. The circuit can be equivalently represented as in diagram C. At this time, the current direction in the load has not changed, and the voltage across the load remains positive. Whether Vs is in the positive or negative half cycle, the voltage across the load is always unipolar. From the above analysis, we can obtain the voltage waveforms across the diode in the load. Compared with half-wave rectification, the load voltage here has a waveform throughout the full cycle of Vs, which constitutes full-wave rectification. If the RMS value of the excitation source voltage is Vs, then the average voltage across the load is about 0.9 Vs. Since each diode conducts for only half a cycle, the rectified current flowing through each diode equals half the load current. The maximum reverse voltage a diode withstands equals the amplitude of the excitation source voltage. When selecting a diode, its maximum reverse working voltage should be greater than this value, and its maximum rectified current should also be greater than the calculated rectified current here. Of course, the diode's maximum operating frequency must also be greater than the excitation source's frequency. The simplified form in diagram D can also be used to represent the bridge rectifier composed of 4 diodes, with the diode symbols indicating the rectification direction. Currently, many packaged bridge rectifier products with only 4 pins are available for selection. If the constant voltage drop model of a diode is used for analysis, assuming the forward voltage drop is 0.7 volts, then the diode conducts only when the absolute value of Vs is greater than twice 0.7 volts. At this time, the voltage across the load is smaller than that obtained using the ideal model, and the maximum reverse voltage across the diode will also be reduced by 0.7 volts. A diode can also form a limiter circuit. Let's look at this circuit. If the ideal diode model is used, the circuit can be represented as in diagram B. It can be seen that only when the input voltage exceeds VREF will the diode conduct, with zero forward voltage drop. The output voltage is clamped at VREF, otherwise the diode is cut off, equivalent to an open circuit, and the output voltage equals the input voltage. If the input voltage is a sine wave and its amplitude exceeds VREF, then the output voltage waveform will be as shown in the figure, corresponding to the solid line in the diagram. The circuit limits the output voltage to a value less than VREF. The maximum reverse voltage across the diode equals the amplitude of the input voltage plus VREF. Of course, it is also easy to calculate the maximum forward current when the diode conducts, allowing the selection of a suitable diode. If the constant voltage drop model is used for analysis, the circuit can be represented as in diagram C. In this case, the diode conducts only when the input voltage exceeds VREF plus VD, and the output voltage is clamped at this sum. Otherwise, the diode is cut off and the output voltage equals the input voltage. The result using the constant voltage drop model differs slightly from that of the ideal model, but the circuit still limits the output voltage within a specified range. Next, let's study the switching circuit. Two input voltages take only two values, 0 volts and 5 volts. Using the ideal diode model for analysis, we can see that as long as one of the two input voltages is 0 volts, a diode will conduct and the output voltage will be 0 volts. Only when both input voltages are 5 volts will the output be 5 volts. The table lists the input-output relationships for all cases. This relationship is commonly referred to as the AND logic operation in digital circuits. Small signal application. In this circuit, the DC voltage source VDD is 5 volts. Vs is a small signal sine voltage source with an amplitude of only 0.1 volts. The resistor R equals 5 kilo ohms, and in the constant voltage drop model, the forward voltage drop of the diode is 0.7 volts. Find the AC component and total value of the output voltage and plot its waveform. According to the superposition principle, considering only the effect of the DC voltage source, we obtain the equivalent circuit in diagram B. This circuit is also called the DC path. Since VDD exceeds VD, the diode is forward biased and conducting. The DC output voltage is 4.3 volts, and the DC current in the loop is 0.86 milliamperes. This current is the Q-point current. Based on the Q-point, we can then use the diode small signal model to analyze the situation under Vs. The equivalent circuit is shown in diagram C, with the DC voltage source removed and the diode replaced by its small signal model. Here, RD is the diode's dynamic resistance at the Q-point. Based on the Q-point current, the dynamic resistance of the diode is about 0.03 kilo ohms. From diagram C, the AC component of the output voltage can be obtained. The total output voltage is the DC value plus the dynamic AC component. The waveform of the output voltage can thus be drawn as shown. The concepts of the DC path and small signal equivalent circuit mentioned in this example, and the method of dividing the problem into quiescent and dynamic cases for solution, are very important. They will be frequently used in the analysis of amplifier circuits and require due attention. In addition to analyzing diode circuits using simplified models, the graphical method can also be used. The graphical method does not require concern for linearity or nonlinearity, but the prerequisite is that the diode's characteristic curve is known. Below, we use this circuit as an example to introduce the graphical process. When considering only the DC voltage source, we obtain the equivalent circuit shown in diagram B. On the right side of the red dashed line is the diode's current voltage characteristic curve. On the left side of the dashed line we can write the circuit equation. This equation in the characteristic curve's coordinate system is a straight line. From the intersects of this line with the coordinate axis, we can draw the line, and its intersection with the curve is the quiescent operating point, Q point, from which the corresponding quiescent current and voltage can be obtained. When the small signal Vs is added, the circuit equation on the left side of the red dashed line now includes Vs. Based on the original quiescent graphical analysis, when Vs reaches its positive peak and negative peak, the straight line will shift to the positions of the upper right dashed line and the lower left dashed line, respectively, and the intersection point of the line and the curve will move from point Q to Q prime and Q double prime. It can be seen that under the action of the excitation source Vs, the changes in diode current and voltage can be obtained. In fact, replacing the curve segment between Q prime and Q double prime with a straight line is precisely the diode small signal model we introduced earlier. Different usage conditions require different simplified circuits and analysis methods. This tells us that nothing is unchanging. Flexibility and timely adjustment according to actual conditions are necessary to achieve optimal results. That concludes today's lesson. See you next time.